Hi everyone, welcome back to Dave's Math channel. I'm your host David Tare, and this is my fourth video in the subseries of on derivatives of my series on first year calculus. Today I'm going to talk about another differentiation rule, a very important one, the product rule, also known as Leibniz rule. And it's stated here, but I'll get into this in more detail. Anyway, let's begin. So here's the products rule, like I said, also known as Leibniz's rule. It's named after the second inventor of calculus, Gottfried Leibniz, who invented calculus independently of Sir Isaac Newton, um, and use the notation we're using on this slide. So here's what it says. It says if you have any two differentiable univariate functions, f of x and g of x, then the derivative of their product, which we write as d dx of the product f of x times g of x, is just f of x times the derivative of g of x, f of x dg dx, as we write it here, plus g of x times the derivative of f of x, or g of x df dx. That's what it says. So it's a little more complicated than the other rules we've been learning, but not too much. Anyway, so let's do a proof similar to the kinds of proofs we were doing earlier. So again, we can use the definition of a derivative as a limit to prove this, and the proof is a little bit complicated, but not too bad. Let's just go through it. So let's let capital F. This is kind of like the proof I did in my last video on linearity. Same idea. So we let, in this case, we let capital F of x be the product, little f of x times little g of x. And then we just use a definition and plug away. So let's see what we get. We get capital F prime of x. Now I'm using Newton's prime notation. So f prime of x is equal to the limit as h goes to 0 of capital F of x plus h minus capital F of x over h. That's nothing but the definition of a derivative of capital F. So now let's simplify this expression. And now I'm just going to, on the second line, I'm plugging in what capital F is. So remember that capital F is just little f times little g. So we replace capital F plus h, f of x plus h, with little f of x plus h times little g of x plus h. And then we're subtracting capital F of x, which is little f of x times little g of x. And then we're dividing the whole thing by h. Now we do a little trick here. This is where things get a little bit tricky, but it's not a very complicated trick. I think once you see this trick, you'll kind of know how to do it again if you need to. So now what we do is we do something that looks a little weird. We actually add and subtract the same thing. We actually make the numerator a little bit more complicated. And you'll see why we're doing this, I think, below. But here's what we're doing. We have already the numerator, but now we're going to add and subtract the same term that wasn't in there before. We're going to first subtract little f of x plus h times little g of x. And now we're going to add it back, plus f of x plus h times g of x. You might wonder why we did that. Well, I think you should notice something a little interesting here. First of all, remember that the limit of a sum is equal to sum of two limits of the same thing. I think I mentioned that in my last video. It's a pretty obvious fact. I'm not going to bother proving it. It's pretty easy. You can prove it yourself if you want, but it's pretty obvious. So anyway, we're just splitting up the limit on line 3 into two limits. We're just splitting up the sum. So we have the limit as h goes to 0 of little f of x plus h times the quantity. And now I'm also using the distributive property here. So I'm really just simplifying the first two terms on the line 3, in the numerator of line 3. I'm using the distributive property. So we factoring out little f of x plus h. And now what we're left with is little g of x plus h minus little g of x. Now this should start looking a little bit familiar to you. And we're dividing the whole thing by h. And then we do the same thing for the other side. This time, we factor out for the last two terms in the numerator on the third line, we can factor out little f of x. And when we do that, we're left with, I think I made a mistake. Yeah, it looks like I did. No, I did. We're factoring out little g of x. So little g of x gets factored out of the last two terms, and we're left with little f of x plus h minus little f of x. I had to reverse the order. Maybe that's why I got a little confused here. But anyway, that's what we get just using the distributive law. I think you guys can see that. Now, it should be kind of interesting because you know that the limit of a product is also equal to the product of two limits. I think I mentioned that last time too. So we can factor out the limit as h goes to 0 of little f of x plus h from the left side, from the first limit. That's a trivial limit, by the way. I mean, the limit is h goes to 0 of f of x plus h. You might as well plug in h equals 0. That's just f of x. That's what we're going to get on the last line. But now let's look at the term next to it. Now we still have a limit here. The limit is h goes to 0 of g of x plus h minus g of x over h. Well, I think you guys should recognize this now. This is nothing but g prime of x. This is just a definition of the derivative of g at x. So we're going to get f of x times g prime of x for the first term in the sum. And now the second term, we can factor out g of x. We don't even have to take a limit of that because there's no h on it. So we're factoring out g of x, and now we're left with the limit as h goes to 0 of f of x plus h minus f of x over h. Well, once again, that's nothing but the definite derivative of f of x. So that's just f prime of x. So when you're done with all this, look what you get. You get f of x times g prime of x plus g of x times f prime of x. That's exactly what we wanted to prove. That is the product rule, or Leibniz rule, if you like. So that's the proof. You know, a little messy, but it gets things done. And if you don't like that proof, there's a much easier kind of visual proof. This is the proof you usually see in textbooks. And, you know, they say a picture's worth 1,000 words. The reason I didn't show this proof to begin with, you have to back up a little bit. You have to use something called differentials. I haven't talked about differentials yet. du. I mean, here we're working with two quantities. I guess instead of f of x and g of x, we're calling u. Just think of u as another variable. So u is like f of x, and v is like g of x. And then du, what do we mean by that? You're supposed to think of a small change in u. Remember, du is sort of like delta u, except we're letting delta go to 0. We're letting delta u go to 0. So imagine you have two quantities, u and v. We don't really care about what they are, but we have these two quantities, u and v, and they could be functions. I guess they're functions of what they're calling t in this slide. Don't worry about that. They're just using a different name for the independent variable. Instead of using x, using t. You can think of t as time, if you like. I think I did talk about speed in one of my early videos on limits. So a lot of times we do take derivatives with respect to time. As a matter of fact, speed's a good example of that. Speed is the derivative of position with respect to time. And acceleration is the derivative of speed with respect to time. So you will see derivatives with respect to time. You might as well see them here. So anyway, just imagine we have these two functions, u of t and v of t. And, you know, they both depend on time. So imagine that u grows a little bit. It grows by du. And du is supposed to be small. It's supposed to be infinitesimal. So now, look, and let's compute the area of this big rectangle. Well, it says u times du plus v times dv. Now you can, you know, use FOIL if you like. If you do that, you're going to get uv plus udv plus v du plus du dv. But we don't care about du dv. I mean, that's a product of two differentials, and that's like second order, so that kind of goes to 0. I mean, I know that sounds a little confusing, but when you're done with all this, the difference you get. So what you're going to get is, you really want to know the difference between the area of the big green rectangle and the little darker green rectangle in the lower left corner. So the darker rectangle obviously has area u times v, uv. So remember what we had for the big rectangle? We had uv plus udv plus v du, but now we're subtracting uv. When you do that, you're going to get udv plus v du. And then you can think about taking derivative with respect to time. All you're doing is dividing everything by dt. So du dt, the rate of change of u is really just the differential of u divided by the differential of t, the differential of time. I know that sounds a little weird, but just think of it as the limit is delta u delta t go to 0. So it's really delta u over delta t, which does kind of make sense, but then you're letting those get small. That becomes du dt. So using differentials or infinitesimals, they call them here, you do also get, you can also prove the product rule this way. And I think this way, I hope I haven't confused you guys. I know I haven't talked about differentials yet. But this is at least a little bit more of an intuitive proof, I think, than most people prefer this proof to the one I just showed. But there are two different ways you can prove the product rule. You can choose whichever one you prefer. And anyway, that is another proof of the product rule. And I just want to finish with an example. So this is kind of a nice example, I think. Let's let f and g both be powers. So let's let f of x be x to the a and g of x be x to the b, where a and b are both non-negative integers. And we already know how to differentiate these functions because I did a video on the power rule a few days ago. So now we can, let's just for fun, calculate the derivative of the product. Capital F, let's get capital F of x be little f of x times little g of x. That's just, you can simplify this. This is just x to the a times x to the b. And you know that exponents, when you multiply, two things raised to an exponent, you just add the exponent. So x to the a times x to the b is just x to the a plus b. But we also find n to be a plus b, so it's just x to the n. So again, capital F is another power. And we can use the product rule to evaluate its derivative. And if we do that, let's just apply the power rule that we just learned. So you would just write down what it says. Capital F prime of x is little f of x times little g prime of x plus little g of x times little f prime of x. Well, now we can substitute everything. Little f of x is just x to the a. And we already know how to differentiate powers because I did it already. So since g of x is x to the b, g prime of x is bx to the b minus 1. So on the left, we're going to get x to the a times bx times x to the b minus 1. On the right, we're going to get g of x, that's x to the b, times f prime of x, and that's ax to the a minus 1. Now we can simplify this sum. Notice that both terms are multiplied by x to the a plus b minus 1. Again, we're taking the product of two powers, so we're adding the powers on both sides. I think you can see the power, the exponent is a plus b minus 1. And the terms in front are a and b, so we're going to a plus b times x to the a plus b minus 1. But remember, n is equal to a plus b. So we can write this whole thing as nx to the n minus 1. Well, we could have gotten this result just by using the power rule for capital F of x. But, I think this is a nice example because it shows that there's not always just one way to solve a problem. I think in this case, it would have been easier just to use the power rule directly for the product. But you can also see that you can get it using the product rule. And this is a little bit of a sanity check. This should give you more confidence that the product rule is correct because it works for this particular case. That doesn't prove the power rule, but at least for a particular case, we know that it works. So I think it's kind of nice to see examples like this. Anyway, that concludes my video on the product rule. Thank you for watching. Long live math, and I'll see you guys next. Bye.